Thank you, Shirshendu. Thank you. So we were at that point that yesterday I recalled the proof of the observability of wave equations under GCC on an open subset, right? I gave you I reminded the short argument by microlocal analysis, and in particular by using the Egorov theorem. And then we were at that point that I was asking the question, now, what happens if you try to remove the assumption that the subset on which you put the observation is open? Now you assume that it's only measurable. Of course, we will assume that the measure of small omega is positive, of course. And we would like to know what can be said. So let us, always for the wave equation, let us first investigate the easy case of one dimension. Because in the one-dimensional case, everything works. You have observability in time large enough for any measurable subset of a positive measure. It's known since a long time, since the 70s probably, although maybe I have not seen it written properly in the papers, but it's so easy. So it's a result which is like that you can, I think, almost find in the big paper by Russell, you know, this big survey in 78. The result is that if you do consider the 1D wave equation with Dirichlet boundary conditions, so x, the variable x here ranges between 0 and p, okay? And t is the time. The result says that you take a final time capital T, which is more than 2p. You take any measurable subset, small omega, of the domain 0p, which is measurable, and which is of positive Lebesgue measure. Then you always have observability. I mean, there always exists a positive constant, which is the observability constant that we defined yesterday, such that this observability inequality holds true for any solution of the wave equation. And the proof is extremely easy because it just consists of looking at a Fourier expansion. So we expand any solution of the wave equation with respect to the corresponding eigenfunctions of the Laplace operator, the sign of Jx, right? With the coefficients that are cosine and sine in time. So as usual, as we said yesterday, the coefficients Aj and Bj stand for the initial conditions of the wave equation. And the sum of the squares of the coefficients Aj and Bj give you exactly, up to some constant, of course, give you exactly the square of the norm of the initial condition, right? Now, you take this Fourier series expansion and you plug it into the energy functional. And you compute, you expand. So first thing that we will do, we will use the fact that t is greater than 2p, so that the integral between 0 and capital T is greater than the integral between 0 and 2p. First obvious thing, right? Now we take this energy and we expand. We expand the series phi. So this gives you a double series, right? There are two indices, j and k. And you have crossed terms, right? So for instance, you see you have this crossed integral, which is you take the coefficient in time number j times the coefficient in time number k. And separately, you multiply by the integral of the crossed modes, sine of jx, sine of kx, integrated over small omega. But now the miracle of Fourier series, as you know, is that since you integrate on 0 to p, all these crossed terms vanish. As soon as j is different from k, the integral is equal to 0, of course, right? So the double sum becomes a single sum where you sum only on the diagonal terms. And so you are left with the sum over all j of aj squared plus bj squared times the integral over small omega of sine square of jx. Okay, now it's not difficult to conclude observability. And there are two ways. I will give you two ways that are both interesting. The first way is to say that, well, you would like to, what you would like to do is to give a lower bound of this thing here by this sum, right? Because this sum of coefficient is exactly the norm of the initial condition. So what you would like to obtain is a uniform lower bound for all these integrals over small omega of sine square of jx, right? This is what we want. So the first way is just to say that, well, sine square of jx converges weakly in L2 to 1/2. It's just writing that the sine square is equal to 1/2 minus 1/2 of cosine 2jx. And then cosine 2jx converges to 0 weakly. And so you are done. So from this weak convergence, it means that for high frequencies, you have a uniform lower bound for all these integrals. And now you just look at the n first, say. Of course, they are all positive, so they have a minimum. And so you conclude easily that there exists a uniform lower bound for all these integrals. Okay? So in this first way, which is completely obvious but already interesting, you can note that we use in a very crucial way an interesting information on the high-frequency eigenfunctions. This is only in 1D for the moment, but you can already think of multi-D. And if you try to mimic such a proof, you feel, and we will see that next, tomorrow and the day after, we'll see next that the high-frequency eigenfunctions play a big role. You have to know something on their limits. In some sense. Yeah? You see it in 1D. In 1D, it's very easy because they have only one limit, which is 1/2. So it's very, very easy. But we will see that in multi-D, it is another story, much more difficult. Okay, so it is a first way to conclude observability. Let us give a second way, which is, according to me, even more interesting. Because in the second way, actually, we are going to obtain an explicit expression for the observability constant. And the second way is to use shape optimization here in a very easy way. What we are going to prove is this lemma, which says that for any subset of 0p, which is measurable, and for any mode, for any j, the integral over omega of sine square of jx is always greater than this quantity, which is the measure of omega minus the sine of measure of omega divided by 2. It's always true. So it's an exercise. Okay, let us do it. It's very, very not difficult, but it's interesting. So to do that, let us prove the lemma. Let us do some very basic shape optimization. So what we do here is that we first fix an arbitrary integer j, right? And we consider this functional for the j fixed. Okay, so we consider the functional, which is integrate over some subset, the sine square of jx. And now what you would like to solve as a shape optimization problem is that you would like to minimize this functional, depending on the subset of omega prime, over all possible measurable subsets omega prime that have a fixed Lebesgue measure, which is the 1 of omega. Okay. Well, so the claim, and it's fairly easy here, the claim is that, well, you look at the shape of the sine square, right, which is oscillating, okay, and you apply the so-called bathtub principle. So you see immediately that this problem for J fixed has a unique solution. There is a unique optimal set, up to 0 measure, of course, which is a level set of the function sine square, and this subset is exactly given by this union of subinterval. It's obvious. You take, you consider all possible minima. It's like that. You have the sine square, which is like that. Okay. You consider all minima of sine square, and then you have to spread some measure, some weights. So you fill up with some water or with some black coffee. You fill up and you obtain level sets. And this is the best set omega, right? You fill up until you reach the good measure. And this is the bathtub principle. You fill up a bath. Well, so this is the unique solution. And now, surprisingly, you compute the value, the optimal value. So you compute the integral of the sine square of Jx over this optimal subset. You integrate, right? So you make a sum, and you obtain this guy. You obtain this quantity that does not depend on J, which is a kind of miracle. And so, since this quantity does not depend on J, you have a proof of the lemma, right? And actually, if you look at again the previous proof, well, if you look at again the previous proof, this gives you the observability constant. So this is why this proof is even more interesting, to my opinion. And you see that nowhere here we use the fact that omega is open. Omega is any subset, any measurable subset. Okay, so it is the situation in 1D, which is very, very easy. Now let us go to the multi-D case. So let us ask the question now, what becomes observability of wave equations whenever small omega is only measurable? Can we you can repeat, please. Ah, yes, but it's much more difficult. Actually, well, you are right. So, okay, this is 0p. Okay. Take omega, which is there, which is an interval. Then you know that the minimal time is less than 2 pi. It is given by a formula with the minimal distance between omega and 0 and pi. Here I do not catch it. No, I do not get it because I used Parseval. If you take a p, if you take a time t which is less than 2p, you cannot use Parseval. And then my proof fails completely. It's much more difficult. And it's interesting, by the way, of course. But I did not do it. So let us go to multi-D. And first, so on this slide, let me recall the definitions, the possible definitions of the observability constant. The observability constant, Ct of omega, you remember, is the infimum of the energy of wave solutions over all possible initial conditions which have norm 1, say. But it can also be written in terms of a spectral expansion. It can also be written as a sum of two half waves. This is what we did yesterday. Right, so this is a reminder. Now, if omega is only measurable, then we have to be very careful. We have to be very careful because take an omega which is, for instance, like a set of rational numbers. Okay? It is everywhere dense, but its interior is empty. What happens in that case? So take an omega of empty interior, and which is everywhere dense in capital omega. So in that case, the situation is dramatic, right? There is because of course on omega interior, there is nothing observable, but on the closure of omega, everything is observable. So there is a big difference between Ct of the interior of omega and Ct of the closure of omega. First, obvious remark, we have to be careful. So maybe we should look at Jordan measurable subset, small omega. What is Jordan measurable? It means, by definition, that the Lebesgue measure of the boundary of omega, here I define the boundary of omega as being the closure minus the interior. Okay? So if the Lebesgue measure of the boundary of omega is 0, then obviously Ct of omega is equal to Ct of omega bar is equal to Ct of interior of omega, right? Because it is an integral. Okay. The integral of, you just have to split the integral, and the integral over the boundary of omega is equal to 0 because the measure is 0. Right. So, okay, this is a first obvious remark, but what we would like to do, ideally, is to relate the positivity of this observability constant to GCC in some sense. So let us look at GCC. Again, let me consider it in what follows only the case of a closed Riemannian manifold. There is no boundary again. Now let me give a name to the quantity that we considered yesterday, which is the infimum over all geodesics of the trace, of the time trace that is let by geodesics inside the support of A. So let me take A, which is a non-negative measurable function, right? Let us look at all possible geodesics, or all possible rays propagating in capital omega. Let us look at A along gamma of t. Let us integrate. Let me, in what follows, this is my definition, let me divide by capital T. Okay? This is just to have units. It's not important. And let me take the infimum over all rays. So this quantity, now we call it LT of A. This is a definition. And then GCC is LT of A positive. Okay? GCC means LT of A positive. All rays meet in a non-trivial way the support of A, right? And so what we have seen yesterday, this is a Burke and Gérard result. We have seen yesterday, and I did the proof that when A is continuous, you have an equivalence between observability, that is CT of A positive, and GCC, which is LT of A positive. We have seen that yesterday. Okay, so mainly, we will have to look at, to study this functional LT for functions A that are not necessarily continuous or that are not necessarily a characteristic function of some open subset. This is what we want to do. So I will comment the theorem. Let me first look at this functional LT over a subset omega. In that case, we take A equal to chi omega, the characteristic function of omega. Let me also give another definition, which will be very useful in the sequel, in the following remarks. I will say that a ray, a geodesic ray, gamma, is grazing omega if, well, you see, if it is along the boundary of omega for a duration of times of positive Lebesgue measure. That is, you have a subset small omega like that, which is in your domain. And I say that a ray, is grazing whenever you have a ray like that. So this is a geodesic ray. And along this interval, I am in the boundary of small omega. And I accumulate some time. The integral is positive. While, for instance, if the ray is just tangent like that to small omega, it is not grazing. Okay, because the integral here is equal to 0. Right? So this is a definition. We will say that a ray is grazing whenever for some part, it belongs to the boundary of omega over a set of times of positive measure. Well, so now, yeah, and of course, you have this obvious remark that if there is no grazing ray, then automatically LT of omega bar is equal to LT of the interior of omega. Right? So you feel that the difference here will come from grazing rays. So you will not be very much surprised by the two first items of the following theorem. The first item is the celebrated Bardot-Slebow and Rauch theorem. It says that if LT of the interior of omega is positive, then CT of omega is positive. Okay, we know that because this condition means that GCC is true for the open set interior of omega. And so you have observability. You have observability on omega interior, and hence for omega, of course. And the converse is wrong. I will give you in a few minutes a number of examples to illustrate the result. The result is wrong. But there is a converse, however, which is this. If you want to have the converse, you have to close subsets. So the converse is, if the observability constant of the closure of omega is positive, then LT of omega bar is positive. Okay? This is the converse. And believe me, you will see with the examples, this is more or less sharp, I believe. In particular, of course, because of this preliminary remark, if there is no grazing ray, then you have equivalence between GCC and observability. So really, the lack of equivalence is due to grazing ray, no doubt. So now it's interesting, you feel that it's interesting to study this functional LT for itself. We can study it. We can study its continuity properties and so on. Of course, it's not continuous, but it may be lower or maybe upper semi-continuous, something like that. It may be continuous only on open subsets or maybe on closed subsets or maybe on bare subsets. There are many possible properties. I did not explore anything, but certainly there is still something to be done. But here, let me point out a kind of strange result, saying that there may be a difference between LT of the interior of omega and LT of the closure of omega. Of course, if, for instance, for the trivial situations where omega is everywhere dense but of empty interior, there is a dramatic discrepancy between them. It's not much interesting. I would like at least to have some minimal regularity of omega. And here what we show, and what I'm going also to, I'm also going to give some examples to illustrate, we show that if you are on a manifold capital omega on which the metric is at least of class C2, and if omega, small omega, is a submanifold C1 of capital omega, so regular enough, right? Then you have this kind of strange inequality. You see, LT of omega bar is less than half of 1 plus LT of interior of omega. And actually, this inequality is sharp. I'm going to illustrate. And for instance, as a consequence of that inequality, if LT of omega bar is greater than 1/2, then because of this inequality, you must have that LT of interior of omega is positive, and therefore, by Bardot, Lebeau, and Rauch, you have observability. Do you see? And I have not many assumptions, okay, on omega. Omega is quite, well, I have regularity, but otherwise omega is quite arbitrary. I just have an assumption on the closure. The closure is big enough in some sense. Then you have observability. Now let me illustrate with some results, with some examples. So I already commented about the first item, LT of interior of omega positive implies observability. This is Bardot, Lebeau, and Rauch. Okay. And as I already said, the critical situation is due to grazing rays. So let us take several examples where you do have grazing rays, just to better understand what can happen. So there is a first example, which is, to my opinion, very, very interesting, which is due to Gilles Lebeau, which is the following. You take capital omega, which is the unit sphere, okay? The unit sphere. And then, as an observation subset, you take small omega, which is the open northern hemisphere, so the part in blue, but open. I mean, you remove the equator, right? Omega is open. Well, the equator is a geodesic ray, right? It is never meeting omega. It is grazing it. It is never meeting omega. And so for every time capital T, LT of omega is equal to 0. GCC is never satisfied, never. However, for every time capital T greater than P, you have observability. This example was given by by Gilles Lebeau in some proceedings paper in French, Journée EDP, Biarritz, where it is also quite sunny, in 92. Now let us, and why is it so? So Gilles Lebeau did an explicit computation. Actually, I can explain you the intuition why it is true. It is because, well, there is only, you see that there is only one geodesic ray that poses problem. This is the equator. So let us focus on the equator. And let us look at the high frequencies of wave equation around the equator. Let us look at high frequencies. What do high frequencies? They oscillate, right? So let me make a drawing, which is only to figure out what happens. So this is the sphere, this is the equator. And let us look possibly concentrating waves around the equator. How do they look like in some sense? Well, in some sense, they look like that. And then if you compute their energies, you observe their energies on small omega, which is the northern hemisphere. So you look at them in this part. What can you observe? You observe half of the energy, right? But half of the energy is enough to observe. And this is why the waves are observable. It's an explicit computation. You can do the explicit computation. It is quite easy thanks to Bessel function in that case. It is what Gilles Lebeau did. And it's already extremely surprising. You don't have GCC because of that ray. However, you do have observability. And if you look at the functional LT, so as I said, LT of omega is equal to 0 for every t. But now if you close omega, if you take the closure, well, LT of omega bar is still equal to 0 for every t small enough. Why? Because you have geodesic rays in the south hemisphere, and they may not meet omega bar, except if the time is large enough, right? Because if you take a ray propagating in the south hemisphere, well, okay, maybe in time less than t, it will not meet the northern hemisphere. But if you let time enough, it will meet. Okay? So this is why LT of omega bar is positive for every time t more than p, which is in perfect accordance with the theorem, right? Actually, you even have, in that case, it's not difficult to see that for every time t greater than 2p, so you have done all the turn of the planet, then the observability constant, or LT of omega bar, are equal to 1/2. Okay. And you can see that, by the way, this example also shows that this surprising inequality I was telling you is sharp. It saturates the inequality. Okay? So this is why I claimed that when omega is regular enough, this inequality is the best possible. Of course, and I think I told it before, but you can have a dramatic discrepancy whenever omega is not regular. You just take here, in that case, you just consider capital omega is the sphere again, but now you consider as an observation subset all the sphere except the equator. Okay? So you take as subset small omega equal to capital omega minus the equator. It does not satisfy the assumption in the theorem because it's not an embedded C1 submanifold. Precisely. And there, you can see that indeed the inequality is not satisfied, but LT of omega is equal to 0, but of course LT of omega bar is equal to 1. Okay. So this shows that the regularity assumptions in order to obtain this inequality cannot be avoided. Let us take other examples, but already this one I like it very much, the unit sphere. Let us take other typical examples that I also like. Now you play chess, you look at checkerboards. So let us consider that capital omega is the flat torus of dimension 2, so the square, but which is periodic. There is still no boundary. So the situation of, in quotes, of deterministic checkerboards was investigated quite recently by Nicolas Burck and Patrick Gérard in 2020. And for instance, what they prove is the following theorem. So you take small omega is a closed checkerboard. So here, for instance, on the left, so small omega is all the blue parts, okay, but it is closed. So omega is the union of all blue parts. In that case, let us look. What is the interior of omega? It is the union of all blue parts, but in which you remove the boundaries of the squares, right? And so in that case, LT of the interior of omega is equal to 0, just because if you take a ray which is grazing the squares like that, then it never meets the interior of omega. Right? So LT of the interior of omega is always equal to 0, whatever capital T may be. Now, since omega is closed, here on this configuration, you can see that LT of omega is positive. Right? And Burck and Gérard prove that indeed, and their proof is absolutely not easy, it's with second microlocalizations. Maybe Belassen told you about that. 2 levels of, it's complicated. 2 parameters. First parameter, you do a microlocalization, and then a second parameter, and you do a second microlocalization. It's extremely technical, but beautiful. And they prove that we have observability. Here, this situation is not covered by the previous theorem I showed you. Because on this situation, you see the surface which is covered by small omega is half of the total surface. So it's the limit case in my previous theorem. It does not work. It does not apply. And there is a second way of looking at checkerboards, which is also investigated in my paper with Emmanuel and Yannick Privat, which is a recent one. So we did random checkerboards. And so what is a random checkerboard? So you consider the flat torus, which is the square here. And you do inside a regular subdivision. And then you take each pixel, okay, each subsquare, and each time you take a subsquare, like that, a pixel, you decide to darken it or not. That is, either you do a black square or you let it white, okay, according to a Bernoulli law with probability epsilon. I mean, so you take each pixel, and then for a given pixel, well, with probability epsilon, I put it in black. Otherwise, I let it in white, okay? I obtain, in such a way, a random checkerboard. What is small n here? Small n is, let's say, the number of squares. Then, of course, and exactly as before, LT of the interior of such a set is always equal to 0, because you always have those limit rays that never meet the interior of the subset. Okay, you take vertical rays, never meeting the black squares when you take the interior. And now, what we prove in the paper is that in probability, LT of the closed one converges to epsilon as n tends to the infinity. It's a convergence in probability. And because of that, we infer that you have, at the limit, you have observability with probability 1. This is what is claimed here. So as you take the limit, it's kind of intuitive anyway, right? You have observability. But I claim that you have observability whatever epsilon may be. That is here. And for every t, yes. Yes, for every t. Yes. But epsilon can be arbitrarily small anyway. The surface covered by the black squares can be only epsilon. Right, so these are examples. Still, let me continue. So for the above item, I already commented it, I think. I recalled the result by Burke and Gerard that GCC with a positive, sorry, with a non-negative continuous function A is equivalent to GCC. Already said it. And finally, let me add a last comment on this discrepancy result, which was the last part of the theorem. So I said that if the metric G is C2 and if omega is an embedded C1 submanifold, then you have this inequality. And I showed you that for the sphere, this inequality is sharp. I told you too that the fact that omega is embedded C1 is important. Otherwise, the result is not true. Now, last thing, also, and strangely, also the fact that the matrix is C2 is sharp. I mean, if you remove the assumption that the matrix is C2, the result fails. And here is an example. So this example is the following. You take a pill. Did you take pills? I'm sorry. So you take a pill. What is a pill? You take a sphere, you cut it in the middle, in the equator, and then you prolong with a cylinder like that. So because there is a cylinder, of course, in this region that is dashed here, the matrix is not C2. It's only C1 but not C2 here. You lose the C2 feature. Okay, so this pill is the, let's say, the manifold capital omega. And now let us choose as an observation subset small omega everything except this dashed region. Okay, so you just remove the dashed region. So the observation subset is very big. Well, anyway, I claim that LT of omega is equal to 0 for every time, but LT of omega bar is almost equal to 1. because you just have to look at the shape of geodesics. Okay. Just have to look at the shape of geodesics. Geodesics have no choice, actually. When they will cross the dashed region, the crossing is quite quick. Except those geodesics that will remain exactly in the dashed region. So this shows that all assumptions in this theorem are sharp. So how such results can be proved? Let me still give some additional results. Let me recall again the expression for the observability constant. Okay? In particular, the last one. Observability constant is the infimum over the energy of sum of half waves over all conditions, initial conditions of norm equal to 1. Right. Well, now let me introduce, you see, a new quantity compared with the observability constant. I will now focus on high frequencies. I mean, why not? Okay. So high frequencies mean I will take initial conditions not having low frequencies. I mean, if you take a Hilbert basis of eigenfunctions, the initial conditions that I do consider here now don't have any component on the n first eigenfunctions. Okay, so it's like in a Fourier series. In a Fourier series, you start the sum at n plus 1. This is what we do here. Okay, you start, I wrote, by the way, sorry. You start the sum at n plus 1. So it defines a new quantity, right? You define it exactly in the same way as before, but now let us denote it by Ct greater than n, and we can call it the observability, the high frequency observability constant. Observability constant for frequencies greater than n. Of course, since Ct of A is an infimum that is taken on a larger set, you must have that Ct of A is less than Ct greater than n. And actually, the Ct greater than n form a non-decreasing sequence with respect to n for the same reason. Because each time you take the infimum over a smaller set. So you do have this inequality. And actually, also, this sequence of observability constants for frequencies larger than n is bounded above, clearly. Okay, you just have to take an upper estimate of this integral. It's obvious, it exists. So the sequence of observability constant is a non-decreasing bounded sequence, and so it converges, right? Let us give a name to its limit. And again, let me divide by capital T. It's not important, but I have to keep constants. So let me define what we now call the high frequency observability constant, which will be denoted in what follows by alpha T of A. It is the limit when n tends to the infinity of those observability constant for frequencies larger than n. So now you have this inequality, right? The initial observability constant divided by T is less than Ctn, which is itself less than this alpha T, which is the limit. Now, you will not be surprised by this result that is boxed here. I do claim, and we are going to prove it, maybe not today, we'll see, that the high frequency observability constant exactly coincides, up to some constants, with the functional LT, which is measuring GCC. And this equality is true whenever the function A is continuous. We are going to prove that. But already you can think about that. It says that definitely GCC, it's not a surprise, GCC is related to high frequencies. But now it's more precise. Before that, it was an intuition. Okay, it's related to high frequencies. No, it's more precise. GCC is related to the high frequency observability constant. And you have an equality for A continuous. So as a consequence, you have this chain of inequalities for any measurable subset small omega. Well, and in particular, if you would like to have the same equality for measurable subset, well, you see, you have no choice. You have to assume that there is no grazing ray. So if there is no grazing ray, GCC and omega coincides with the high frequency observability constant. Okay, there are other items such that this one I will not insist, but it is crucial actually in the proof that it's a bit technical, but if the observability constant, CT, is strictly less than the high frequency observability constant, recall that we have an inequality which is lower than or equal to. But if the inequality is strict, then I claim that the infimum in the definition of the observability constant is reached, which is actually a compactness concentration result, which is important technically in the proof, but I will not enter into details here. And the third fact is that now you take any measurable subset, small omega, of a positive Lebesgue measure, then you have an equivalence between observability, which is CT of omega positive, and positivity of the high frequency observability constant. Again, here, you will not be surprised by this result because look at the proof, look at the short argument of proof. The short argument of proof consists of showing this equivalence by considering invisible solutions, as did Bellassem and as I recalled yesterday. Except that in looking at invisible solutions, you have to be careful because now your subset omega is only measurable. So you have to be careful. In the invisible solution argument, you cannot use microlocal defect measures and so on. No. You have to do another way. You have to do another way, and this is why I said C article, because in our article we have another argument that is not microlocal in order to prove that there are no invisible solutions. And because of that, you can have this equivalence. But now, so I will not prove 2 and 3, but I refer you to the article if you are interested. But we can prove this first equality, which is actually certainly the most interesting. So the fact that the high frequency observability constant coincides with the quantity that quantifies GCC, which is a purely geometric quantity. Alpha of t equal to half of LT of A. I do not, until what time am I allowed to speak? It's now? It's okay? It's finished? No? I don't. Few minutes? Okay, let me see. Let us try. Let us try. Yeah, we can try. In 3 minutes, After 3 minutes, you stop me. So the proof of that follows the same scheme as yesterday. I mean, you look at the energy of the sum of half waves, except that now these are high frequency half waves, right? This is the only difference. So you perform exactly the same as yesterday. In particular, on this part and on this part, you remember you can use Egorov, as I did yesterday. While, oh yeah. Please, 2 minutes. While on this part, you have compact operators. This is what I said yesterday. So there is no change here. There is no change. You just have to look, say, this principal part here, right? And for this principal part, because of this principal part, you see that the observability constant for high frequencies is equal to this infimum. This is the infimum of the principal part, plus a small o, right? Plus a small o as capital N tends to the infinity. So what we have to do is mainly identify this part with the geometric quantity, which is LT of A. That's all we have to do. And this is more or less Egorov, you see, more or less. So slightly, it's almost that. Actually, the argument of yesterday, I mean, applying guarding, gives you one inequality. Applying guarding, and applying Egorov if you want, gives you the inequality in one sense. It says that alpha T of A is greater than LT of A. Now, to prove the converse inequality, what we have to do is choose particular wave equations, so particular initial conditions, so that at the end, at the limit, you will have the converse inequalities. And this is very classical in the literature because what you can choose is initial conditions for the wave that almost generate a ray, like on my figure. And I think, I'm quite sure that Belassen explained you this last week, right? This is the story with coherent states. What is a coherent state? It's an exercise in Fourier analysis. You take a family of exponentials, which is partly Gaussian, so very much concentrated, but also very much oscillating. Okay? You see the oscillation with K here. So these are functions, I repeat, exponentials, so with an energy very much concentrated somewhere, but very much oscillating. Now, if on these states you compute the quantity there, which is with a pseudo differential operator, then you obtain that at the limit, you have exactly the function A at some precise point. So did Belassen do that? Okay, in any case, you will see, I have given the complete proof if you want in the slides. It's not difficult, but it's quite horrible because you have to compute integrals, many integrals. But it's completely classical. In the literature, you know, these are called Gaussian beams. These are Gaussian beams. You generate particular wave equations that concentrate along a given ray. It's completely classical and elementary, actually. And because of that, so you take this lemma, you apply it to your situation, except there is just a thing to take care of. You have to truncate to high frequencies. I mean, you have to remove the low modes, but it's not difficult. It's done there on the slides. I let you read if you are interested, but this is my claim. So we can stop here as promised.
Thank you, Emmanuel, for the nice talk. Now I ask the audience if they have a question, they can ask. And also in the online, if there is any questions that you can take. Okay, if there is no question, then let us thanks Emmanuel again.